and we will be able to model growth and exponential decay. First thing we're going to start with today is exponential growth. So here's the equation model that we are going to use throughout the day for both growth and decay. A is going to represent your starting amount. B is going to be considered your base. And then your x is going to be your exponent. When we talk about growth, it's important to understand that the base for growth is going to be greater than 1. So that is going to be considered your growth factor, your B value. But when exponential growth, your base is going to be greater than 1. If we take a look, we're just going to look at the pink graph here to start. But this graph shows exponential growth and decay, but we're talking about growth. So understanding that our graph of this equation that we're working on today is going to continuously increase, okay? And with exponential, it's going to increase rapidly or decrease rapidly. So today, growth to start, exponential growth is going to increase rapidly. Let's take a look at our first problem. We know this population of this town is 1,300, and we know that it increases by 1.4% a year. So, pulling out the important information, we understand that x, this is going to be this time piece. What's going to constantly change is this variable here, the x variable. Okay, the y is going to be our population, and a is going to be our starting value, and that's where we start with 13,000 for our population. And b, the base, b, this is the part that we're going to have to find usually each time. To find b, we need to understand that we're taking 100% of my 13,000 and increasing that each year. To truly understand what this is saying, we need to take my population of 13,000, and we know it increases by 1.4% each year. So we need to multiply this 13, the population in 1988, by 1.4% and add it to the 1998 population. 99 would be 100% of your 1988, so this 13,000, 100% of this, plus another 1.4%. So that's where they get this 100% from the current year, which would be 1998, plus an increase of 1.4% for our 1999, and that's going to give us 101.4%. Now, notice we have a percent here, so they have to convert that back. So we have 101.4, and we move it over to decimals, and we get the 1.014, and this is going to be my B value, which you can see right here. Plug in what we know. We start with 13,000, that goes out front, that's my A value. Here is my B value inside these parentheses, and X is going to be the year that I'm trying to find, and that's going to constantly change depending on what the question is asking me. So this next part says what it would be in 2006. Take that formula that we just found, and we're going to plug in 8. Now, why do we plug in 8 here? The reason we plug in 8 is because 2006 is 8 years after 1998, and this was my A value, and that's what was my first amount. So we plug in 8 in for my X, solve it all out, we get approximately 14,529, so we know that it's approximately the population in 2006. We're going to take a look at some interest, which is like our banking problems. So when a bank pays interest on both principal and the interest that an account has, the bank is paying, it's what we call compound interest. And then knowing your interest period is the length of time which interest is calculated. So these two definitions are going to be important for these problems. So compound interest is when the bank is paying interest on both the amount that's in the account, the principal, which is like the amount, and the interest that is being accumulated over time. Interest period is how many times the length that it's being calculated. So typically we're probably going to see more annually, so their interest is accounted for one time a year. You may hear semi-annually is when it's compounded. So then we have to calculate this 2 times during the year. So if my interest rate would be 8%, I would take my 8% and divide it by 2 and understand that it's being calculated with 4% every 6 months, because 6 months happening twice is going to give me my 12 months, which is my 1 year. Quarterly is another way to say to compound interest, to have that, so we'd be calculating it 4 times in a year. So take my 8% divided by 4, so that's going to be 8 divided by 4 is 2%, and then every 3 months, so 3 months, every 3 months we'd calculate it 4 different times throughout the year and give us that 12 months. Where if it was monthly, if interest was compounded monthly versus annually, then we would calculate it 12 times during the year. So we take 8 divided by 4, which give me 0.6 repeating. So this is what the percent value be per month. And these little words are going to help you solve these problems throughout. So here we have a problem here where we are depositing $1,000 into a college fund that pays 7.2% annually, so one time a year. Find the account after 5 years. So pull out our exponential function. What do we know? X is going to be the interest period. Y is going to be my balance. A is going to be your initial, which is $1,000. Now this B part here is, once again, taking what you have, 100% of the amount that's in your account, in that bank account, 100% of that plus another 7.2%, because that is what your interest, the amount of money you're going to receive because of your interest. So 100% of your account plus the 7.2%. We add them together, we're going to get 107.2. Move my decimal to get rid of the percent. And here's the equation we came up with. We want to know after 5 years. So now my X value, we're going to solve for 5. And we're going to find that the account will have $1,415.71. So that will be the balance after 5 years. So let's say the problem previously, let's say we are going to compound it quarterly. So going back to that chart, we know that quarterly means 4 times. So 4 times instead of 1 time annually. So we need to change my B value here. It's 100% plus whatever it is compounded 4 times in a year. So we just take that percent, that 7.2%, that interest part, and we're going to divide it by 4. So if you take 7.2 and divide it by 4, you're going to get 1.8. So now I take 100% plus 1.8%, and you're going to get 101.8%. And down here you can see they've already moved that decimal and gotten 1.018. So that is going to be your B value now. So now, once again, we're just plugging in. So it wants to know after 5 years, well, how many times, if it's compounded quarterly in 5 years? Well, the first year, we're going to get 4 times. It's going to be counted for. So the second year, we're going to get 8. Third year, we're going to get 12. Fourth year, 16 times. And that 5th year, it's going to be compounded how many times? 20 times. It'll be half. So now, we plug in 24x instead of what we did earlier. So punch this all into a calculator and you're going to get $1,428.75. So that'll be the balance after 5 years. So understand that there is a difference between interest being accounted for annually or quarterly. Alright, now we're going to work on exponential decay. So understanding we have the same exact setup here for our equation, except A is still going to be my starting amount, B is going to be my base once again, but now my B is going to be between 0 and 1. That is going to be my decay factor. So now, instead of it being greater than, it's going to be between 0 and 1. So we know when B is between 0 and 1, my decay is going to be going down. Okay, my graph is going to be increasing quickly downwards and then leveling out. So here's the problem. Suppose that the population of an endangered species has decreased 2.4% each year. There were 60, my A value, my initial starting amount of these animals in the year 1999. Write an equation to figure this out. We're going to use that same setup, our exponential function setup. We know x is going to be the number of years, y is going to be the number of animals remaining. So this is kind of that total running. A is going to be 60 here because that is my initial, that is my starting. That happens for both exponential growth and decay. X here, or B, I'm sorry, B is going to be the decay factor. So I take 100% of the amount of animals I started with in 1999, and I need to subtract the amount that is decreasing, that 2.4% that is decreasing. So take 100% minus your 2.4%, and you're going to get 97.6%. Once again, we need to move my decimal because that is in a percent. So move it over to 0.976 is where you'll be at. So now that we know my B value is 0.976, we can write this into my equation. So once again, 60 is my A, my starting value, 60 animals. It is decreasing by 0.976, and then X is going to be the time. So we are asking for in 2005. Understand that in 2005, 6 years has passed since 1999. So I'm going to plug in 6 for my X value. Punch that into your calculator. You're going to get approximately 52. What is that 52 saying though? That means there is 52 remaining endangered species in 2005 compared to the 60 in 1999. I did not do a half-life problem on this video, but if you do have questions on that, you can find it on page 478 of your textbook. That is all for today.